Thank, First of all, I would like to thank organizer for giving possibility to present my talk, and the topic is chiral phonons and micropolar theory of elasticity. Yesterday, lecture was given where electronic and magnetic properties in non-center symmetrical crystals were nicely explained, but phononic system was left beyond consideration. So I try to demonstrate that it can exhibit interesting properties too. The outline of my talk is following. Firstly, I give a brief explanation of basics of the classical treatment of micropolar medium. Then I present quantum version of this theory. Then I give brief introduction to the phonon-Zeeman effect and the inverse phonon-Zeeman effect for centrosymmetrical crystals. Then I present some results concerning the possibility to observe similar phenomena in non-center symmetrical crystals. For this purpose, I give a brief introduction to the theory of electromagnetic fields in the micropolar elastic medium and explain how magnetization due to phonons can arise in this material which initially don't possess such a magnetization. I start with basics of classical theory. The elastic theory we study in universities was suggested firstly by Cauchy, who was first who guessed that we have to operate not but the atomic displacement, but the second rank tensor strain deformations. In the beginning of 20th century, another French mathematician, Jean Casseras, expanded Cauchy theory, and he introduced micro-rotations as independent degrees of freedom from the micro-displacement. For this purpose, he expanded definitions of the Cauchy strain tensor epsilon, introducing the additional term related with rotation. And also he introduced additional strain tensor, Cassera tensor, or Reines tensor, which totally depend on the micro-rotation phi. The strain energy density is expressed like a bilinear form of these strain tensors, and the last term describes interaction between the Cauchy and Cassera tensors. APC tensor of rank depend on point group of crystals, and they can be found in the handbook by Sirotin and Shaskovskaya. The idea to introduce local rotation in medium is not new and can be met in another areas of physics. For example, academician Krylov used this idea to describe dynamic of ships, naval ships, and in this situation, micro-rotation corresponds, sorry, I will explain in Russian. Поперечная качка, значит, килевая качка и рисканье. We were motivated this idea when studied non-center symmetrical crystal from niobium sulfur 6, which belongs to the class of layered dihydrogennates. And this crystal has no inversion symmetry, and we can single out the block of atoms from sulfur 6. And it's rather natural to assume that this block can rotate independently from the common field of displacements. To apply this approach to this crystal, I briefly explain basic equation of the micropolar theory. Beyond the expansion of the strain tensors, we have to introduce additional stress tensor. Of course, we have stress tensor, like shown in the left panel, but also we have to introduce coupled stress tensor, which shows how the momentum of momenta distributed over the faces of the microvolume. Basic equations include so-called equations of balance, which are nothing than Newton's laws for displacement field and rotational fields, where rho is a mass density, g, small g is a micro-inertial tensor, and F is the density of force, L is a torque, external torque, and T and M tensors are usual tensor and stress tensor and the coupled stress tensor. Also, we have to introduce so-called constitutive equations, which relate stress tensors with strain tensors, Hooke laws. And also we have kinematic relations, which express as strain tensors with displacement and rotational fields. Then we can obtain closed system of dynamical equation for the displacement and rotations. These equations are written for the 6 to 2 point group of the crystal from niobium sulfur 6. We can see that in the equation for the transfer modes, there are terms which are linear ingredients. It means that parity is broken in the system, but time reversal symmetry is not. The equations for longitudinal modes are written below, and they contain no such terms. Then we consider propagation of the elastic wave in the micropolar theory, propagating along the principal axis, z-axis, and the results of calculations are shown on the plot. And we see that longitudinal modes shown here by dotted lines contain a gapful branch related with local rotations and a gapless branch related with displacement. And similar effects happen for transverse modes shown by solid red and blue lines. But we see that there is a Rashba effect when these branches are shifted, and they correspond to right circular polarization and left circular polarization, respectively. We also can tune hybridization parameter between Cauchy and Cassera tensors and obtain Roton minimum at the lowest branch of excitations. But special efforts are needed to choose these parameters, because Roton minimum appears only in very narrow range of hybridizations values. Explicit expression for the excitation branches can be derived explicitly, and to our surprise, it was found out that this spectrum totally coincides with that obtained for superfluid gallium in the series of paper by Nazier. And also Nazier introduced, without any explanation, some gapful branch, which hybridizes with gapless acoustic excitations that results to formation of the Roton minimum. So this scenario totally support previous version of theory of superfluidity by Landau before the war, when Roton minimum was centered at 0 point, but Roton minimum at non-zero values appears as a result of hybridization. In his theory, Nazier interprets this Roton minimum as a manifestation of incipient crystallization instability, and proves that Roton minimum never touch zero frequency, because it leads to depletion of the Bose-condensate. In our theory, micropolar theory, similar theorem can be proved, and it can be shown that when rotor minimum touch 0 point, energy functional loss positiveness, this crystal become unstable. It should be noted that micropolar theory gives truly chiral branches of excitations. In contrast to the series based on the displacement only, where definite chirality appears only some parts of Brillouin zone and depends on k vector. Here, whatever k vector we obtain only definite chirality. It can be shown if we introduce the vector of the phonon state composite from the weights obtained from the solution of dynamical equation for displacement and rotations. Then we make projection to the basis of left-right circularly polarized transfer modes and calculate spin phonon operators, which was introduced in paper by Jean-Pierre, and we see that phonon spin is determined by the difference square weights minus and square weight s plus. In our case, branches correspond to either plus or minus, so we take values for phonon spin plus minus h only. Prediction of the rotor minimum attract a lot of efforts from experimentalists because it became clear that rotor minimum does not related with low temperature dynamics, not quantum effect, but related with kinematic and can be observed at room temperatures. First success was reached by a group from Karlsruhe Institute of Technology. Leader is Martin Wegener. They synthesized elastic metamaterial shown here. Wait, sorry. Shown here. This material was done this Chinese guy, Yi Chen. He spent several months to print it. And they measure excitation branches of this metamaterial, and we can easily recognize similarity between the prediction of the micropolar calculation and excitation of this material. We see that there are two gapless excitation branches with rotor minimum and two gapful modes corresponding to local rotations. Also, independently, measurements of piezoelectric signals were performed, and they also confirmed the existence of the rotor minimum. But I have to say that it's harder to expect in real crystals the appearance of the rotor minimum because it requires very specific values of hybridization parameters. This is why they have to create artificial material. But for us, more important that there are gapful excitations in the spectrum. Now I present the result of quantization of the micropolar theory because it will be needed for us to construct analog of inverse Zeeman effect. The steps are standard. We take dynamical equations, introduce Lagrangian density, then define Hamiltonian, introduce primary quantization, second quantization. Here, the key points that we have to take two boson fields separately for displacement and rotations. Then we obtain boson Hamiltonian, which contains hybridization parameter k, determined by coupling between Cauchy and Cassera tensors. And applying Bogoliubov transformations, we get diagonal form, and eigenfrequencies totally coincide with results of the classical theory. As appropriate, we get operators for the displacement and the rotation as a function of k vector, expressed via the quasi-particle creation annihilation apparatus. For transfer modes, situation much more interesting. If we construct a Lagrangian density from the classical equations, we see that two specific terms appear here. They contain terms linear ingredient over the rotational fields. This is nothing but Lifshitz invariance. So if we are dealing with a spin subsystem, we would say that micropolar theory introduces Zoloshinsky-Maury interaction to the series. So using of micropolar theory is quite natural for non-center symmetrical crystals. So we then construct Hamiltonian. Again, we develop some secondary quantization representation for displacement and rotation via Boson operators A and B. Again, obtain hybridization, Boson Hamiltonian with hybridizations. Here, hybridization parameters contains component of C foreign tensor. Here, the Foyt notions are used, and there is a hybridization also related with Cauchy strain tensor only. Again, we have to apply Bogoliubov transformation to diagonalize this form. It's rather routinious work, but nevertheless it can be done, and obtain diagonal form. For our further purposes, it will be useful to introduce linear combination of the Bogoliubov coefficients. Here, the notions are taken as follows. Big U means that in long wave limit, displacement dominates. Big phi means that in long wave limit, rotations prevail. And AO means gap is gapful, optical, and plus minus means in polarization. Also, there are useful constraints for Bogoliubov coefficients that simplify further calculations severely. Excitation spectrum obtained via Bogoliubov diagonalization also coincide one-to-one with result of classical theory, and we again obtain quantum expression, quantum operators for displacement and rotations of given wave number Q and definite polarization plus minus. Here in the right-hand side, we see the big Q, big F coefficients and quasi-particles of the diagonalized spectrum. Time dependence is these expressions enter-wise time dependence of the Boson creation and annihilation operators as usual. And now I briefly explain what phenomena we expect for non-center symmetrical crystals based on the results available for center symmetrical crystals. Phonon-Zeeman effect. This effect was opened in the middle of 70s by Schock, who applied external static magnetic field to the rare earth halide rift or 3. I don't know how to pronounce it, I guess. And later it was found that a double degenerate dipole active optical modes splitted by this magnetic field, like Zeeman splitting of spin 1/2 states. And later it was found that these states circulate polarized, and the theory of this phenomena was suggested 2 years later by Thalmeier and Fulde. It's based on the transition between the levels of the crystal field of rare earths with an account of magnetoelastic coupling. After some decades, new interest to this phenomena arose after discovery of the multiferricity. The story started with a famous paper by Katsura Nagawa-Sapalatsky, who predicted appearance of the static polarization field in the material with non-uniform magnetization. For example, magnetic spiral can produce polarization field. And later, inverse effect was predicted if polarization field vary with time, it can produce magnetic moment. And nice explanation of these effects was given in the review by Urashek and al. 2017. Main explanation of this phenomenon is based on this microscopic picture. Atoms rotate around their local position, and this rotation will generate magnetic moment, like shown here. But problem is only that this magnetic moment is proportional to nuclear Bohr magneton. So additional mechanisms needed to explain proportionality, for example, to electronic Bohr magneton. But I later will discuss this. Several years ago, analog of this effect, not related with the ground state like in previous slide, but related with phonons-Zeeman effect was revealed. Here, instead of using of the static magnetic field, they apply the pulse, laser pulse, and instantly split, lift the degeneracy of the phonon modes, and it results to oscillating magnetic moment like this due to fast oscillation of the nuclear vibrations of different amplitudes. This effect, this effect, which can be called inverse phonons-Zeeman effect, when lattice dynamic cause appearance of the magnetization, should be different from the so-called inverse phonon Faraday effect, which is beyond the lattice dynamic. For example, it can be realized in this material shown here. It's based on dynamical evolution of the ground state. For example, if you have magnetic cycloid spreading over the p-axis, it will produce polarization field along the a-axis. If you apply a pulse of electromagnetic field, it will stir the polarization vector, and due to this relation, it will lead to appearance of the magnetic moment along the p-axis. This is not our case. We will see analog of this effect. Here, the table summarizes all experimental finding of phonons-Zeeman effect. It can be seen that all crystals used in these experiments have no inversion symmetry and exhibit no piezoelectricity as a consequence. Natural questions then arise whether we can expect analog of such phenomena in non-center symmetric crystal, and our answer is positive yes, and I explain how we can obtain. For this purpose, we have to develop a electrodynamics of inner field in micropolar medium. And this subject was considered by Nowatzki 40 years ago from Poland, and he could derive a constituent equation which relates inner polarization field with external electric field. External electric field, external strain, and additional rotational fields determined by these expressions. They contain local rotation and displacement using the tensor form for 6 to 2 point group. We can obtain equation for P plus polarization as a function of displacement and rotation. We can see that there is a longitudinal polarization component too. Having enhanced quantum expression for the displacement and rotations, we obtain a quantum operator for polarization operator plus minus q, where time dependence enters via the exponential factors. This cartoon show how physics evolves when elastic wave propagate along the axis. It will generate two oppositely rotating polarization field plus minus, and I will demonstrate now that it will cause longitudinal magnetic field. To calculate magnetic field, we have to use Maxwell equations for initially non-magnetic material. Magnetic field produced by time-varying polarization field, like first equation. So we can easily find that two oppositely rotating B plus B minus component existence this material, and we can obtain operators of magnetic field of definite polarization plus minus and of given wave number q. And then we can introduce phonon state which carries magnetic wave p plus minus q and calculate inner product for zero temperature. The result is given here. And taking square root, we obtain measure of observable magnetic field. And the plot here show Q dependence of magnetic field. We see that no inversion symmetry exists, and but this operation Q to minus Q relates B plus Q and B minus Q. Also, logarithmic singularity is available at small q, and analysis of this expression shows that local rotation contributes, related with depthful excitations, contributes to this singularity. This picture of elastic waves and generated electromagnetic fields allow to introduce very naturally the measure of chirality in this crystal, because in theories which don't invoke micro-rotations, there is a problem how to determine chirality, and artificial construction based on vector field of displacements was used. But here, naturally, we can introduce so-called Lipkin-Zilch, some conservation law in Maxwell equation opened in 1964, and this Zilch can be written via magnetic field and dot p. Applying the Fourier transformation, we can calculate observable value of Zilch Q component on the ground state, phonon ground state, and see that it is determined by the difference between B plus squared and B minus squared. So dynamical piezoelectric wave which generate a finite magnetic chirality rooted in the lattice symmetry. Also, there is a problem in centrosymmetrical crystal. How to explain that magnetic moment measured in the experiments is order of electronic Bohr magneton, because theory can explain rigorously only proportionality to nuclear Bohr magneton. So they artificially invoke additional interaction to transfer moment from a nuclear subsystem to electronic one, and these are various types of spin-orbit coupling. In our approach, this problem resolved very naturally. We can consider interaction of spin with two circularly polarized field, and the problem can be solved within Floquet analysis. I skip needles. We can apply so-called high frequency expansion. It's valid if spin has zero energy and frequency of rotating magnetic fields is very high, is order of 10 terahertz. So we can construct perturbation scheme and derive effective Hamiltonian. Details can be found in this review, Goldman and Dalibor. Effective Hamiltonian shown here. We see that resulting magnetic field along the z-axis appear, and again, it is determined by the difference between squared B plus and squared B minus. We have effect of the spinning top here. And this can be supported for for system with itinerant electrons too. because previous Flocky theory can be applied only to insulators. But here we have to require that itinerant electrons shouldn't screen piezoelectric wave. It can be provided if frequency omega bigger than plasma frequency. It leads to limitation for concentration, and this piezoelectric scenario is valid only for lightly doped semiconductors. So we can consider this problem through the model Hamiltonian, where circular rotating magnetic field and polarization field are included via the vector potential, the scalar potential, and the simplified version of this Hamiltonian given by this expression. B plus B minus field here acts like spin flip scattering potential. This Hamiltonian can be considered like was done by Ira and Sanderson when they studied conductivity in spin density wave and obtained energy system. Like my time is out. Sorry, my time is out. Sergey shows that I had to say stop. But anyway, we can calculate magnetization. And again, here the factor P plus squared and B minus squared appears. So difference of this rotating field will cause finite magnetization along the axis, even in conducting system too. Now, here is shown how to count splitting of electron subsystem via the Paul crash pattern.
Yes, Sasha. Maybe we'll
and
discuss.
This is estimation of P, how to relate value of magnetic moment per elementary cell with inner magnetic field. If we see in the experiment this value, it will correspond to these quantities. Yes. It's very reasonable. No giant fields are needed to get realization. So I won't voice my conclusions. This picture show how effect appears. We have non-magnetic materials excite external pulse elastic wave. It will generate magnetic field along the z-axis, and resulting magnetic moment appears along the z-axis. So a steep. This is done in collaboration with Japanese colleagues, Professor Kishino, Professor Satan, and my postgraduate students.
Yes.
Thank you for your attention.
All right. Yeah. Of course, we are definitely off the time, but well, in fact, this is extremely hot topic, and I specifically asked Sasha to prepare this doc, and you see that it's really overwhelming. But and he started a little bit late, so I would still allow for a couple of questions. Yeah. So we have these two. So maybe Sasha will start, and then Vadim. Yeah.
Давайте я все-таки по-русски.
Да,
Вопрос сложный. Лучше на этом языке. Вот понимаете что? Вот вы хотите связать движение довольно тяжелых ионов с магнитным полем. Механизм, очевидно, два. Орбитальный и спиновый. Орбитальный, по-моему, очень плохо, потому что масса ужасно тяжелая у ионов. И эффект тоже будет малый. Что касается спинового, вам, наверное, нужна для этого еще спин-орбита. Потому что иначе вам не удастся. Это еще хуже.
Так,
Ну, подождите.
да.
Казалось бы, уж если играть в эту игру, то можно было бы посмотреть следующее обстоятельство, что магнитное поле, оно значительно лучше влияет на движение электронов. Они легкие, и поэтому с ними нормально. И если, в принципе, вы учтете за счет электрон-фононного взаимодействия влияние электронов на фононы, да, так сказать, вот таким образом, казалось бы, так можно что-то будет получить, хотя я не уверен, потому что это не тематические должны быть поправки тоже. Вот вы не могли бы прокомментировать силу и вот сопоставление разных механизмов?
Вот на сегодняшний день теории-то и нет. Вот я сейчас скажу, я понял. Тут вот не надо все-таки путать, что мы сейчас микроскопический механизм для центросимметричных кристаллов, которые сейчас считаются, и вот где вот то, что вы сказали, абсолютно верно. Вот здесь на самом деле никто не считал вот эту проблему. Сейчас вот так делаем с микро. Вот. То есть мы в нашей теории. Щас, чуть-чуть. Нет, вот материальное уравнение. Вот у нас все же основано на вот этом материальном уравнении P, которое связывает со смещениями. И вообще проблема-то сейчас актуальная. Вот посчитать тензоры вот эти, да, X, гамма, и с первых принципов.
Вадим,
Ага.
не, можно я чуть... можно я чуть-чуть...
А
даже-
это не...
Вадим,
И симметрия это не ноль. И симметрия это не ноль.
я чуть-чуть хотел бы ответить.
Да.
На самом деле прокомментировать. То есть буквально пару недель назад появилась классная работа совершенно китайская. Вот один из авторов должен был приехать, но не приехал. Лижанг. а, Лифан Жанг. Вот. Но они что сделали? Они вот именно то, что вы говорите, включили электрон-фононное взаимодействие. Это не центросимметричные кристаллы, как правило, да? И у них появился тот же самый альтермагнетизм, только в фононных зонах. И, как я их понял, это именно эффект электрон-фононного взаимодействия. На недиабатичности, да. То есть вот то, что вы говорите, это очень-очень разумно, и вот буквально только что было сделано.
Да, у меня совсем простой вопрос, извините. Значит, вот если перейти от хиральных фононов к движению реальных атомов, да, то есть вот реальных ионов, если они делают, так сказать, не такие просто вот полукруговые какие-то качения, а полный круг, то, казалось бы, значит, это означает, но на языке таком классическом, вырождение по энергии и просто зануление локальной жесткости с соседними, значит, атомами, какими-то рвутся пружинки, да, то, что крутилось. То есть я хочу сказать, что если сделать из шариков и пружинок вашу картинку, ну, механическую, то есть нет у вас там квантового туннелирования, то есть пробовал ли кто-нибудь, ну, просто вот руками сделать шарики, пружинки, и, соответственно, из шариков пружинок вот закрутить атом, тогда пружинки какие должны рваться. А второй маленький тоже под вопрос. Значит, вот что касается нецентросимметричных, то какие должны быть нецентросимметричные? То есть, скажем, совсем простые нецентросимметричные, типа P20 и кубическая симметрия, как марганец кремний. Будут хиральные фононы или нет? Спасибо.
Ну, давайте я на второй вопрос сразу отвечу. Там вот есть телур, да, вот он децентросимметричный, вот, и вот как раз для него вот один из моих вот соавторов, так, он как раз теорию опубликовал, значит, там они обошлись без микрополярной теории, то есть они там полностью на смещениях работают, вот, да, тригональный, да, и там они вот как раз для оптических мод вот альтерномагнитные моды получают. Вот, то есть там можно вот сделать, но там и непонятно, как микрополярную теорию, значит, использовать, потому что это материал. Вот, и там вот для микрополярной теории надо, чтобы неоднородность какая-то была. Ага, ага. Ну, а там что в телуре? Там они все расположены на такой, как бы, ну, спирали, да. Еще дополнительно совершают локальные вращения. То есть там, вот если картину вот построить фанонных мод, вот там она вот так вот выглядит. Да-да-да, вокруг своих, как бы, таких, ну, э, позиций.
Ну хорошо,
А
похоже...
вот первый вопрос, вот вы спросили, кто-то применял вот такую механическую модель. Вот в 86 году, да, Буш, кажется, да, вот, он сигнетоэлектрика рассматривал, и там как раз они увидели в нейтронном рассеянии оптические моды, которые не могли быть объяснены вот, ну, как в рамках традиционной теории упругости. И они как раз использовали микрополярную теорию, показали, что это как раз вот щелевые вращения.